So now that we're experts at limits, we might be interested to know that they connect to an idea that we've already seen before, and that's this idea of continuity. So we learned last year that a function is continuous if it's like a nice smooth curve with no breaks in it, right? So the definition that I gave you last year is that continuous means you can draw the graph of the function without picking up your pencil, right? So no jumps or breaks in it. Now that we have a firm understanding of limits, we can make that definition better, so more specific. So as we look through these examples, we should see a pattern start to emerge. So first example is a function where the limit as x approaches 2 does not exist. So that means that the left limit and the right limit are not the same. And that might look something like this. We have this point x equals 2. And maybe we have some kind of break. And you can draw your own example just as long as we have this jump in the graph. And then the question is this function continuous? And this is, of course, not continuous. So right away we're noticing if the left and right limit are not equal, then the function is not continuous, right? And that shouldn't be super surprising if we think about what this means. Okay? Now we want a function where the limit exists, but f of 2 does not exist. So that means the function is not defined, but my curve otherwise meets up at that point. So something like this, if this is x equals 2, you'd have an open circle. Make sure your circle is open circle at x equals 2. Okay, so this means that my left and right limits are equal to each other, so the limit of f of x at 2 exists, but f of 2 is undefined. And obviously, again, because we have this hole, this is not continuous. Okay. And here, this is the most complicated one, right? So limit exists, f of 2 exists, but they're not equal. So what that means, right, is we can draw the same graph that we drew before, but then we can draw a filled in point somewhere not on the curve at 2. And this is again, so this right here means my limit is not equal to the function value. This again, of course, is not continuous. Okay? So now we have 3 cases where we know that if something is true, the function is not continuous, right? So either the limit doesn't exist, the function doesn't exist, or the limit is not equal to the function. Okay? So what this gives us is a 3-part definition of continuity. Okay, so the 3 parts definition is function is continuous at a point. So we need 3 things to be true. The first thing is the limit at that point of the function exists. And make yourself this note. You already know this, but make yourself this note. That means that the left limit and the right limit are equal. Okay, so the limit exists. The function exists at that point. So a is my point that we're looking at. So we'll say f of a is defined. And the third point, f of a is equal to the limit at a. So the reason that we need this definition, that we're studying this definition, is 1, we live in a continuous world. So it's good to be specific about that, what that means. And 2, you are graduating to the point in your math career where it's important to be able to prove things in a rigorous way. Okay? So that means logically, we're going to say, if these things are true, it's impossible for the function not to be continuous. So that's why we need these 3 parts. And if you look at the graphs, right, the logic is quite clear. That if any one of these things is missing, the function cannot be continuous. Okay? So that's our key takeaway here. The main idea is that if any one piece of the definition is not true, the function can't be continuous. Okay, that's my key takeaway. So once you have that and the rest of the notes, we'll do some examples of proving a function is continuous. Okay, so what we're looking at now is a piecewise function, and our goal is to analyze the continuity of this function at -2. And notice -2 is the boundary where our two pieces might meet up. So the way we're going to do this is we're going to reference the definition. And you are now in the phase of your math career where you're making an argument. You're no longer like solving a problem, solving for X. You're making an argument about whether or not something is true. So this is similar to in science, if you've done claim, evidence, reasoning types of responses. This is exactly that. But our evidence now is our mathematical definition. Okay, so the way we're going to do this is we're going to use the three parts of the definition. So I need to know whether the limit exists, whether the function exists, and whether they're equal to each other. So to show whether or not the limit exists, I need to consider the left and the right limits. The left limit is going to be what I get when I plug in -2 to this lower piece, and the result here is -2. The right limit is going to be what I get when I plug it into the other piece, the upper piece, the greater than 2 piece, which is also -2. So that means that the limit exists and is equal to 2. -2, I should say, right? So I've shown that that limit exists now, so check. Now, f of -2, well, that's what I get when I plug it into the or equal to piece, right? So I've already calculated that. I know that that is also -2. So that also exists. And then I need to check to see whether or not they are equal. And they are, right? So I would say that this limit is equal to f of -2 is equal to -2. And then I've shown, I have 1, 2, 3 parts. I've shown by showing that these three things are true, that f is continuous at x equals -2. And this, by the way, is exactly what you would need for your points on an AP Calc FRQ. Number 6 is an example that is not continuous now, and we should note that we're looking at x equals 2, although it's obvious that that would be where the discontinuity would have to be. And the reason for it is the left limit is not equal to the right limit and is not equal to f of x. And you can pause and check if you want, but these are my left and right limits. So I could say that the limit does not exist as x approaches 2, and so f is not continuous. Okay. So it does not meet this definition. And then I don't have to check, because we know that I don't have to check f of 2, although that one is easy, because we know that all three parts of the definition have to be true. So if one is not true, then we don't worry about the rest of them. Right, the last thing we can run into, values of k that make the function continuous. So I need the limit as x approaches, we're looking at 1 obviously, to be equal to the limit as x approaches 1 from the right of f of x. Okay, well, that means that I need the limit as x approaches 1 of the left-hand piece to be equal to the limit as x approaches 1 of the right-hand piece. Now I can just plug this in. So k squared minus 12, and then 1k. And make sure that's an x and not a k. That's a common mistake. And then this is math you know how to do. So those are the values of k that make f continuous. So this setup, though, comes from that three-part definition. So it's useful in a number of ways here.